The directions say to evaluate the line integral where c is the given plane curve. In example 1, we have the integral over c of y ds. And c is defined by the following parametric equations. X equals t squared, y equals 2t, where t is greater than or equal to 0 and less than or equal to 3. So we can note that dx dt is equal to 2t, dy dt is equal to 2. ds is the square root of dx dt squared plus dy dt squared dt. And so this is equal to the square root of 4t squared plus 4 dt. And now we're ready to make our substitution. So the integral over c of y ds is the integral from 0 to 3 of. Now remember, if we go back, y is equal to 2t. So I get to replace y with 2t. That's right here. ds is the square root of 4t squared plus 4 dt. And my limits of integration are going to be from 0 to 3. And now we can solve this integral by u substitution. And so I'm going to let u equal 4t squared plus 4. du is 8t dt. So t dt is 1/8 du. Now, when t is 0, u is equal to 4. So I plug it into this equation right here. When t is 3, u is equal to 40. And so the integral from 0 to 3 of 2t times the square root of 4t squared plus 4 dt becomes 1/4 the integral from 4 to 40 of square root of u du, right here. And so this is equal to 1/4 times 2/3 u to the 3/2 evaluated from 4 up to 40. But remember, 1/4 times 2/3 is equal to 1/6. So what I'm going to do is also replace the u with 40 and replace u with 4 and subtract the results. So I'm applying the fundamental theorem of calculus. And so on the second line, we end up with 1/6 times the quantity, 40 to the 3/2 minus 4 to the 3/2. Okay? So this is 1/6 times the quantity, 40 square root of 40 minus 8. And so remember, 4 to the 3/2, this is equal to the square root of 4 raised to the 3rd power. But the square root of 4 is 2. So this is 2 to the 3rd, which is equal to 8. So that's how that came about. And also remember, square root of 40 is the square root of 4 times 10. But the square root of 4 is 2, and so this can be written as 2 times the square root of 10. And so remember, 2 times 40 is 80. And so on this line here, we get 1/6 times the quantity, 80 times the square root of 10, minus 8. And if I factor out that 8, the very last line, we get 4/3 times the quantity, 10 square root of 10 minus 1. And I would expect somebody in Calculus 3 to be able to simplify it down to that very last line. That's example 1. Let's take a look at example 2. This one's the integral over c of x squared y plus sine of x dy, where c is the arc of the parabola y equals x squared from the ordered pair 0, 0 to the ordered pair pi, pi squared. Now, here's the typical way we parameterize a parabola. So what I'm going to do is I'm going to let x equal t. So then y equals t squared. Remember that x is greater than or equal to 0 and less than or equal to pi. But because x is equal to t, that tells me that t is greater than or equal to 0 and less than or equal to pi. Now, we need to know dy. Well, if y equals t squared, then dy is 2t dt. And this is all substitution all the time. And so what I'm going to do in this line integral is replace x with t, y with t squared, and dy with 2t dt. And I also want you to keep note of these limits here. So on the next page, the integral over c of x squared y plus sine of x dy is equal to the integral from 0 to pi of t squared times t squared plus sine of t, that quantity, times 2t dt. So to go from the first line to the second line is straight substitution. And so don't forget, x is equal to t, y is equal to t squared, and dy is 2t dt. And so all I did was straight substitution. And then on the third line, to get this line down below, I break up the integral because it's easier to manage. And so this is the integral from 0 to pi of 2t to the 5th dt plus the integral from 0 to pi of 2t sine of t dt. Now, let's take care of the first integral first. So to evaluate the integral from 0 to pi of 2t to the 5th dt, we get the following, right? So the integral from 0 to pi of 2t to the 5th dt is 1/3 t to the 6th evaluated from 0 to pi. And if I replace t with pi, I get pi to the 6th divided by 3. That's the first integral. Now let's take a look at the integral from 0 to pi of 2t sine of t dt. So this is classic integration by parts. I'm going to let u equal 2t, du is 2 dt, dv is sine of t dt, and then v is negative cosine of t. So the integral from 0 to pi of 2t sine of t dt is uv, which is negative 2t cosine of t evaluated from 0 to pi, minus the integral from 0 to pi of v du. So in other words, you're going to end up with plus the integral from 0 to pi of 2 cosine t dt. Because don't forget, my v du is here, and v is negative cosine t. And when you subtract a negative cosine t, that's really adding cosine of t, right? And that's where that plus comes in. And so, again, you get plus the integral from 0 to pi of 2 cosine t dt. So remember, cosine of pi is negative 1. So when I replace t with pi, I get negative 2 pi times negative 1. That's right here. And then I go plus 2 sine of t evaluated from 0 to pi. But remember, if I look at sine of pi, that's equal to 0. And then sine of 0 is equal to 0. And so this piece ends up going away. And I'm just left with 2 pi. And so the integral over c of x squared y plus sine of x dy is pi to the third over 3 plus 2 pi. And if I get a common denominator, I get pi to the third plus 6 pi over 3. And that's example 2. Let's look at example 3. Suppose we have the integral over c of x e to the y ds, where c is the line segment from 2, 0 to 5, 4. So the typical way you parameterize a line segment from one point to another is the following. So xy, the ordered pair xy, is 1 minus t times the initial point, which is 2, 0, plus t times the terminal point, which is 5, 4. And t is between 0 and 1. That's the restriction on t. And if you notice, when t is 0, you get the ordered pair 2, 0, because that second term drops off. When t is 1, the first term drops off, and you get the ordered pair 5, 4. So if I take this a step further, we're going to equate the x components and equate the y components. So x is 2 times 1 minus t plus 5t, which is equal to 2 plus 3t. Y ends up equaling 4t. Now, dx dt is equal to 3, dy dt is equal to 4. So that's going to allow me to find ds. So here, let's backtrack here. ds is the square root of 3 squared plus 4 squared dt, which is equal to 5 dt. So I'll put it here. Now, the integral over c of x e to the y ds is the integral from 0 to 1. Now notice, I'm going to replace x with 2 plus 3t. So that's where x is. That's here. Straight substitution. Y is equal to 4t. And then ds, that's this piece, is 5 dt right here. So this piece is ds. And remember, t goes from 0 to 1. So my lower limit is 0, my upper limit is 1. And so this is equal to the integral from 0 to 1 of 10 plus 15t, that quantity, times e to the 4t dt. And then I just did this one by parts. I treated it as one solid integral. And so I let u equal 10 plus 15t. du is 15 dt. dv is e to the 4t dt. So v is 1/4 e to the 4t. And so when I made my substitution, the integral from 0 to 1 of 10 plus 15t, that quantity, times e to the 4t dt, is equal to 1/4 times 10 plus 15t times e to the 4t, evaluated from 0 to 1, minus the integral from 0 to 1 of 15 over 4 times e to the 4t dt. So this is 25 over 4 e to the 4th minus 10/4 minus, and then when I integrate 15 over 4 e to the 4t, I get minus the quantity 15/16 e to the 4t, evaluated from 0 to 1. Applying the fundamental theorem again, this is 25 over 4 e to the 4th minus 10 over 4 minus 15/16 times the quantity e to the 4th minus 1. So I just pulled the 15/16 out in front. Now over here, I get 25 e to the 4th over 4, or 25/4 e to the 4th, minus 10 over 4, minus 15/16 e to the 4th, plus 15/16. So it does look like I distributed the 15/16 back in anyway, which is fine. And I have to be mindful of that minus sign. And so when I simplify down, you can see I get 85 e to the fourth minus 25 over 16. So the other two lines, I just get a common denominator of 16. I rewrote every term with the 16 in the bottom, and then I simplified accordingly. So all these line integrals are straight substitution. All substitution all the time. That's what I tend to tell my class. All right. That'll do it for this video. I did 3 examples on the line integral. Okay. Thank you.